Electron affinity, how much an element wants an electron. If the number is higher, it means how badly the element wants the electron. Elements take in electrons willingly to become stable and try to fill up their valence shell, or the last electron shell. Noble gases are an exception to this rule because they don't care about gaining an electron. Their valence shell is already filled, so it becomes a negative ion. Let's take a look at an element with the highest electron affinity. Fluorine. It's a halogen, and all halogens are very energized because they are trying to become an electron to fill its energy level. Fluorine is the first halogen, and this is important because it has less amount of rings. The nucleus plays a big role on why the halogens have a different level of electron affinity. There are only 3 orbitals in a fluorine element. The nucleus, which is made of protons and neutrons, are like the sun. They are a magnetic pole on the orbital. Because the valence orbital is the closest to the nucleus and all the halogens, the nucleus can have more power and demand more for an electron. An example of an element with the highest electron affinity is fluorine because it is an unstable element that only requires one more electron for it to stay stable. Fluorine's electron affinity is 328 kJ/mol. What can affect the electron affinity? There are 2 factors that can affect the electron affinity: the atomic size and the atomic number. When the atomic size of an element is smaller, the outermost shell tends to be closer, meaning there will be a stronger reaction between the nucleus and the new electron. This will cause an increase of the electron affinity from the bottom to the right of the column. Nuclear charge also affects electron affinity by the protons found in the nucleus, which is the atomic number. Since protons have a positive charge, the majority of protons an atom has, the greater the attraction will be between the nucleus and the incoming electron. This will cause the trend of electron affinity to increase upwards from left to right across the periodic table.